Now, we are in the part of the lectures where we show examples for the different types of cable-stayed bridges. We started last time with precast concrete beams. I showed you the Pesco-Kennewick and the East Huntington Bridge. Today we go on first with an example for a cable-stayed concrete bridge with a cast-in-place beam, and then we show an example for a cable-stayed steel bridge. We use as an example the bridge across in Norway, the Helgeland Bridge across the Lier Fjord. The bridge is located at the west coast of Norway, very close to the polar circle. Across the deep fjord, we see here the geology. We have a fjord which is not shown in its full depth. It's actually 120 meters, but that would have made the model too thick. It's a very steep fjord, of course coming from the ice ages where the glaciers have eroded the very strong, hard rock there, and we went smack onto the edges in order to have the minimum possible span length. Now, polar circle does not mean that it is there extremely cold. The Gulf Stream, which heats all Europe, is there also active, and the low temperatures are not significantly lower than they are here. The problem, however, are the very strong winds, especially in winter in the north of Norway at the west coast, at the North Sea. There are very high, very often occurring storms, and they were the main problem for the sizing of the bridge and for the construction itself. Now, what does strong storms mean? We have listed here, we have a 50-year probability assumed that was in accordance with the Norwegian codes, 50-year probability for the final stage, and for construction a 10-year probability, that's shorter. And the wind speed, the reference height, as you may remember from our lectures on dynamics, is at plus 10 meters worldwide, but we are interested especially at plus 50 meters, which is the height of the beam, 50 meters above the sea, and there we have the 10-minute mean 50, but the gust speed, which is the highest fluctuating wind speed with at least a length of 3 to 5 seconds, well, that's the catcher here, 70 meters per second. If we multiply that by 3.6, we come to, without a machine, 252 kilometers per hour. So 250 kilometers per hour storm, that's something. You will not stand up in it. It blows you. And we have pictures of all that. So we can remember 250 kilometers per hour wind in the occurs, and if we say, okay, the construction takes place, say 2 years in this case, now we don't need the full 50-year for the final stage, we just take a 10-year probability. That's something you have to agree with the client or the code states. And it's not much less. If we compare the figures, it's about 10% less. So we still have 225 kilometers per hour. High wind speed, often occurring. And in addition, we have a high turbulency. Now, turbulency is if we have a base wind speed, and then we have the fluctuations about this basic wind speed, and the percentage of fluctuation to the base wind speed we call turbulency, and regularly that's in the range of, say, 5 to 10%. Now here we have 25% turbulency, which is unknown. So we have a very strongly fluctuating wind, which comes, in actual fact, in the direction of the main wind speed. There is a mountain range called the Seven Sisters. There are 7 peaks, and that causes, with the wind blowing over these peaks, causes the heavy turbulency. So that's the problem. And how to show wind in a photography? Difficult. Now, I always like to show this. During construction, there was one of these storms, and this is the water spray. There's a regular water, and all this is spray which is taken up by the storm. So you can imagine what type of storm that is if you have up to the beam level, 50 meters high, spray from the water. That was there. Now, the bridge itself, due to the geology I showed you, had a minimum length of 425 meters. We wanted, again, because of the strong winds, a low as possible beam, so we have little wind resistance or wind action. So we chose 1.2 meters, which for a 425 meter main span gives a slenderness of 1 in 354. There is one a little bit slender in the world, but this is, for this condition with the heavy storms, is exceptional. And I must say, looking back, I did that very much myself with hands-on, together with Dr. Kovac for dynamics, important, and my supervising engineer, Mr. Hopf. We 3 did it mainly. It was a very daring design. It was very bold, and I'm not sure I would do it again today with these, but it worked out all right. And the other interesting thing is, at the polar circle, there's very little traffic. So for the traffic requirements, 1/2 lane would have been sufficient. Now you cannot build a bridge with 1/2 lane, so you need at least 2 lanes plus a walkway and pedestrian. So we have a width of 12 meters. And this again, the ratio to main span to width, 425 to 12, is about 1 in 36, which is also very slender and is dangerous for wind transversely because of the reattachment of the vortices. It's too short. The vortices don't reattach and damp the thing. So very, very slender dimensions both ways. Of course, we have an A tower. I've done in a calculation example, I think in lecture 9, I've done a forerunner of this. There we had only 1 meter beam depth and so on. I've made as a calculation example, and I've shown how the eigenfrequency and torsion goes up if we use an A tower instead of a tower with vertical legs. Briefly, the loads. Again, all this is, as an example, by hand in lecture 9. I've shown all these effects. We have an increase due to theory of second order, nonlinear or P delta effect. If this is linear, then under surface load we have an increase of something like 1/3, 30%, due to nonlinear effects. And in the ultimate limit state, where we are cracked and the beam is less stiff, we have an increase in moments from linear to nonlinear by about 50%. And that also shows you we are here at a limit, because that goes up exponentially, and when you go beyond this, it goes up very fast. So you cannot be more slender either from statical nor from, in this case, wind resistance than this 1.2 meter beam. When we have to design the beam in concrete, it means basically the reinforcement and or the post-tensioning. Then we have to take into account two principal loadings. First of all, in the final stage, when the bridge is completed, now there we have that's 0 here. We have the big positive moment at the center of the bridge. I showed you how to calculate these. About the same here in the quarter. And then we have a bearing here. The moments go down to 0. And these are the negative moment, indirect moments in the final stage. If a track stands here, we get a negative moment inside. Okay, we know that. But then we have to look what happens at the same section during construction. And there we have, in principle, two situations. First of all, we have the situation that we have forwarded the traveler, cast the concrete, and the cables are not fully stressed, which gives us tension at the top, which is here. And there we can see this stage during free cantilevering is governing against the final stage. Just imagine, free cantilevering, put a load on the tip, the thing goes down, the tip goes down, tension at the top, more than in the final stage. So, construction stages, you see the yellow line, are virtually governing in tension on top, negative moments over the full length of the bridge. On the other hand, the positive situation occurs when we have cast the element and we stress the cable to its final force, which means we stress it too much for the actual situation. Then we have tension at the bottom. Now, this is not as bad, and you see here in the middle, where we have the big positive moments in the final state, that's the construction is not governing. The construction moments are more or less constant, but they govern here in the middle, tension at the bottom, where we have very little because of the bearing there in the final stage. So this is fairly typical, the ratio of governing moments, moment envelopes, final stage and construction. You can vary that by all ways, but that's typical. Now, dynamic loads, I will make it brief. This is now, I have given you in the dynamic lectures the theory behind all that. Now this is, here it has been done, of course, everything by computer simulation. And just give you an impression. There's a special publication out by Kovac and me where this is all in detail. It's in the script, so if you want to know more about it, go there. Basically, this is how the computer simulates the wind. We see here the basic wind speed, and here with the fluctuations for the turbulency. Then over the length of the bridge, we create a wind climate. These are 0.2 second steps, how the wind changes. There are 6 runs of, I think, 200 seconds or so, where different wind climates are created, which are placed onto the bridge, this theoretical wind, which is okay in the boundaries as measured on site. And as a result, we then have the bridge oscillating, vibrating, and we can see all the dynamic effects. So these basic phenomena, which I've lined out to you, are applied, of course, by very intricate computer calculations, and this just gives an impression what comes out there. We have taken into account the nonlinear characteristics of all sorts, which means, first of all, the cracking of the concrete, but also nonlinear buckling effects, tilting, kippen, tilting. All these effects are in there, and then we come for sizing. with a moment curvature, kappa we usually use for curvature. This is the curvature, and these are the corresponding moments. This would be linear if we would have steel anti-yield. But here, taking into account the actual reinforcement, the actual post-tensioning at every cross-section, we come to this, and all this is fed back into the computer and run again until we get it stable. And then comes out an interesting phenomenon, which I just show here as an example. We have here the length of the bridge. Here are the towers. And we have horizontal moments from wind transversely onto the beam. And we show here the moments at ultimate stage, where we have used a load factor of 1.6 and calculated it all with the nonlinear effects. And this line shows, the dotted line would be the moments under service load times 1.6, meaning the linearly increased service loads compared with the nonlinear calculated ultimate loads. And we see here in the middle of the main span, interesting enough, that the ultimate loads with nonlinear effects are smaller than the live loads and the service loads with times 1.6. Why? Well, basically, the reason is because we have a cracked beam. We've taken that into account at the ultimate stage. Cracking doesn't occur at service. With cracked concrete, that becomes weaker. We have a redistribution of moments from the center to the towers. So the nonlinear effects can have a reduction as a result. Not everywhere here it's bigger, but this I always thought, and we've looked into that very carefully, why we didn't believe it at the first time, but it's true. So just remember, cracking, as you know, in a continuous girder, can lead to redistribution of moments away from the softer spots to the hard spots. In addition to all these huge computer calculations, the client said, well, that's all very nice what you calculate there, but we want to see it in detail, hands-on. Beautiful. So we had to make a full model, scale 1 in 200, about 2 meters long, dynamically correct, which is not simple, and put it into a wind tunnel. We see here a picture that's about 1.5 meters high. Can that be? 60 divided by 200. No, it's about 50 centimeters high and 2 meters long model picture here. Very nicely detailed. This shows a detail of this wide as a hand beam in there with all, these are the instrumentation to measure all the things, and the cables are nicely simulated. You can do that only very limited. We say use a section model to get the characteristics, a pattern model, 1 in 20 or so. There you can detail, and then you use the results from there in a computer calculation, as we did. The scale does not permit to really show the details. In addition, the kinematic density of the air cannot be changed. So it's of questionable value, I say. But for a client who doesn't understand any mathematics, he believes in that. So the result anyway tallied very nicely. For the Helgeland Bridge, it came out that any flatter phenomena would occur only at very much higher wind speeds, and the governing for sizing, governing loading was buffeting, which means the wind which has different velocity, and we have the gusts, they bang against the beam sometimes in period, and they are That's the governing loading, not aerodynamic instabilities. But it was the important investigation for the bridge. I can tell you it's 220-meter free cantilever, 1.2 meter high in very high storms. But it worked, so what? Now, we come to the construction. In up to 30-meter deep water, it was very strong, hard rock, was cleaned up, and then with divers, a first layer of concrete was placed. I was always impressed, the civil servants who overlooked the construction there, they went down, one or two of them, in diving gear to inspect the underwater concrete themselves, and it was cold, but they were divers apparently, so they went down. Then the tower legs were built from precast boxes on shore, shipped to the site, lowered down with a floating crane onto this base, stressed together. The bottom part was filled with concrete because we needed additional weight for the foundations to prevent tensile stresses underneath the foundation. Klaffende Fuge. Das ist kein Wort im Englischen. So to prevent tension there, and also because we had to cater for ship collision, and there we also needed the loads. Up was hollow the boxes as usual. This is the tower layout, 70 meters, only 2.2 meters wide, and in general 40 centimeters wall thickness. Cable anchorage in concrete in the top, steel pipes for anchoring the cables cast into the concrete. We see here starting of the sliding construction above water. Normally we do not like sliding formwork. We use jumping forms where we go, you know the difference. That's constantly sliding, and jumping is after 3, 4, 5 days. Because with the sliding platform, it's difficult with the built-in items, and we have bad weather and all that. But the Norwegians are world-class concrete engineers and contractors, and they can do it. I mean, this bridge, 425 meters, would in most countries of the world be in steel, built in steel. Not Norway. Norway, they do concrete perfectly, and they could do well with sliding forms also. We see here going up. This looks a little bit untidy. What it actually is it's some insulating sheet hanging down from the sliding forms to protect the young concrete from cold wind. So and there were heating elements actually, and so the concrete was cured for the first time with this part. Here we see from the tower crane a view into the forms coming up. We see here the cloth pin type tower from above. As I said, placing of the built-in items with sliding forms is a little bit tricky, and we need exact locations of the steel pipes for cable anchorages because we need the anchor points precisely. So what we did is we proposed, and the contractor built, steel frames from channels in this instance, where the steel pipes were rigidly welded to. And these frames were put section-wise, one on top of the other, and the reinforcement was installed around. So whatever happens, we have a rigid steel frame into which the steel pipes are welded, and they cannot shift whatever happens during casting. This is the completed tower head we see two types of opening. We see here the steel pipes coming out to cable anchorage, and here we see the anchorages of the loop tendons which connect the two stay cables we will see later. Now, beam construction. We have a double T-beam with outer main girders, 1.2 meters deep, and a 40 centimeter roadway slab. And we have cross girders only between cable anchorages at 12.8 meters, something like that. So this spans here 10 by 12 meter, 40 centimeter. We have transverse post-tensioning only in the cross girders. This is just reinforced, but highly, and we didn't need any more. New trick we used for the Helgeland bridge are the precast elements, but especially their purpose I will explain later. So the stay cable anchorage is a precast element. Here we see it in elevation, and here we see it in a longitudinal, in a sectional view. It's a precast element which is placed into the forms here and cast in. And the purpose for that is we wanted to use the final cables also during construction as support of the 12-meter long traveler during casting. We didn't want to use auxiliary tiebacks, which had to elongate it and all that. I explained that to you in an earlier. So here we found a way the first time to use the permanent cables. How to do it? Well, we can do it by using this precast element, bolt it to the form, and then attach the final cable at its final position and connect it with bolts to the form. And once you can stress it, the concrete is cast and hardened, you loosen the bolts and go to the next element. But in order to have the final stay cable anchorage ready before casting the concrete, you think about it, and we thought about it quite some time until we came up with this solution. The only way, or one reasonable way, is to use a precast element that's there, bolt it to the form, then you can do it. Now, here we see such a precast element. Here will be later the stay cable anchor head coming through, and that's the pockets, the cutouts for the transverse post-tensioning. Here we have an elevation of the formwork traveler, the already completed beam, the new beam, the lower form. There we have the precast element which we bolt to the lower form, and then we have still one little problem. That is, when we stress here the cable, we not only have a vertical component but a horizontal one. How do we get the horizontal component catered for? We had another precast strut which we placed in here, which takes the compression force from the cable into the already completed beam. All that is cast in. So that was the trick, I say, we used here. Because that was all a little bit involved, the contractor built a fairly big size, that was about 1.5 meters or so, off the traveler to see that he could do all the various works which had to be done there and nothing is in the way. And here finally is the beauty which we put much thinking into in action. And we see here the final cable installed. Now we had one little hiccup, and that was when everything was said and done, the site people said, well, we need some shelter here with that cold wind and all that we can't work in, and we need to protect the concrete. Oh, so we need to put here some protective plane. And Kovac, our dynamics, said, No way. We are at the end, and I cannot accept an additional wind load on this wind protection, which is substantial. So what did we come up with? We said, okay, we use here some, I call it flimsy plastic sheets. So when the high difficult wind comes, it's blown away by the wind. So when we have the governing wind, that thing is gone. So that was a solution for under regular condition we have the people and the concrete protected. And under high storms, when we have the governing loading, bending transfers on the beam, Kovacs was satisfied it will not be there. So you have to think up sometimes solutions if you go to the limit. A look into the forms, back to the already cast beam. We have here the precast element, we have the steel pipe cast in, and here's this strut which takes the compression component from the cable. And here we look into the same down from the tower. We have here already installed the next final cables tied back with a strut. And we have the protection which was supposed to fly away so that Kovacs could sleep again. Here we see the form traveler from underneath. We have here the underside, we have a cross girder, and to move it forward, the lower form had to be lowered, the whole traveler went forward and up again. Now, construction started with building the towers. First one completed, this one on its way, and the approach bridges with span wires launching formwork. Starter element was part of the formwork traveler, was connected to the tower to cast the first piece, and then the travelers completely were installed like here, and on we go. We needed one auxiliary pier in the side span, not for vertical reasons but for horizontal reasons. If we have wind blowing on one cantilever much more than on the other, which cannot be included, then we get a horizontally rotating moment, and that was something the tower couldn't take. So we had this auxiliary pier here which has a vertically sliding connection. So it takes only horizontal forces but not vertical, because otherwise we would have a hard spot in our elastic supports and we would have a kink of moments and all that. So that's where it was. At the end of construction it was detonated and served as a habitat for the fish. So we go on with free cantilevering. Finally we close the center joint with one traveler. First traveler is taken down, the second traveler is built across the joint. Then during construction we have a minimum post-tensioning which is coupled in every joint, 8 tendons here, and then when we close side span joint and center joint we thread in additional tendons in this region of high moments. After closing the bridge and T equals infinity, meaning for the shrinkage and creep taking place over the life of the bridge, the beam goes down by 405 millimeters, nearly half a meter, and the tower tips come to the inside, outside, depending where you are, by about 200 millimeters. So what we did was we built the beam by these 405 millimeters too high, and we built the tower here 146 millimeters, or we pulled it back. We built it, of course, vertical, but we pulled it back here with the cables and here, and after shrinkage and creep, hopefully, we have vertical towers and the beam on the desired elevation. In very early lecture 3, I think I've shown you how that works with shrinkage and creep in combination. It's all a little bit involved, but you can remember for a big bridge, 0.5 meter, it can go down. Now, stay cables, parallel wire cables, you know all about it. The first ones we had for corrosion protection after installation, we had cement grouted. Now here at the polar circle, in winter, it was too cold for the cement grout. So for the first time we used some petroleum wax, which can be inserted in a shop and is flexible enough that we can still use reels to transport the cable on site. But once it's installed and the sun is burning on it and the temperature goes down to 40, 50 degrees, it does not become fluid, because otherwise it would build up a hydrostatic pressure and we could get a big bulb and it could crack. So this is the trick. I like to say it has a consistency of chewing gum, something like that. It's flexible, but it's not fluid. So, and then we have the usual anchor head. The cable comes on reels and is anchored, is pulled up to the anchor head, to the tower head, passive anchorage. And in the tower head, it's anchored on the compression plates here of these steel pipes. In plan, it's like this. So how to take the cable forces, the horizontal components we take with loop tendons, overlapping loop tendons, and the vertical force is inserted by itself, so to say, into the concrete. Now, how do we get the cable force into these loops? We use a strut and tie model, Fachwerkmodell. Strut and tie model, and 1/2 of the cable force goes in direct compression struts into the end anchorages, and the other half of the cable force is taken by the radial forces from the loop curvature at both ends. And that's the way how we take up the cable force. Now, pulling it up, then at the beam with a come-along hoist grip, a grip hoist, we pull first the cable near to the anchorage. You see here, precast element, steel pipe, and no concrete yet. You remember, we use the final cables for supporting the traveler. So we install it before we've concreted. Going through here, and now we look at it from underneath. The pull rod or tensioning rod goes through. There's a check chair, there's the hydraulic check with which we pull the cable. I've given you all that in detail before. Cable showed oscillations. So what we did is we tied them down with tie downs, strands, which works quite nice but has two distinct disadvantages. A, it doesn't look nice. B, it makes it difficult to inspect the cables by a carriage which runs onto the stay cables. So we'd rather avoid it by using hydraulic or friction dampers at the bottom, things like that. But here, that was decided. So that's the bridge with the tie downs, not too nice, I think. We therefore use, I'll show you later, the pictures which were taken before those tie downs were installed. Then the bridge looks much nicer. The bridge was instrumented after it was completed for wind speed and direction, for accelerations in bending and torsion, for deflections. And very interesting, this table, I think, I've never seen anything else anywhere else. These values compare the calculated values with the measured. And if it says here 99.99, it means the measured value came 99% to the calculated. It's amazing. So, for various storms, you see here the storms February, March, and January 94. Mainly these heavy storms are in winter. The horizontal response of the beam was checked, and it's for these heavy storms here in the 90 region. The vertical response is about the same, 25% difference between, wind reaction actual and measured is very nice, close. And also the dynamic cable forces, also under these oscillating loads, were higher than 25% higher than anticipated. It wasn't a problem for the safety because that was only for a short time. There was no life load under these storms on the beam. So that's what we learned. But the wind reactions with these very, very intricate, partly newly developed by Kovács for this bridge showed the behavior of the bridge very nicely. And I mean, if I sometimes talk of voodoo dynamics, I never used the word again when I saw the comparisons that it really works. I didn't mean it really, but sometimes to make a joke within us. Okay. The completed bridge, just a few pictures. Now, the opening was attended by the Norwegian Crown Prince, a high occasion. It was on 21 June 1993, which is, as we all know, Midsummer Night, which at the polar circle, the sun doesn't set. In winter, it hardly comes above the horizon at the polar circle, but here there was a big festivity the night through, and I think 3 or 4 o'clock in the morning we went on board the Hurtigruten, this postal ship line which goes up there. And, we had beautiful weather. It was a very nice open festivity. And here during that occasion, the bridge, I think, for its only time in its life, saw a traffic queue. It will never occur again, but it did during opening. And here a picture of the bridge in longitudinal view and the completed bridge. So I don't think I have to summarize a lot this time. I just showed you all the steps to build a cast-in-place concrete beam in a very, I will not say adverse climate, that's not the proper word, but with very strong storms. But with proper care, very tedious calculations and thinking about construction, we could do it. And afterwards, I must say, I'm glad it worked all right. There were people said it will not survive the construction, it will come down. But we were quite happy, and so this is about the limit you can go with cable-stayed bridges. Thank you.